This is chapter 9, chemistry. We have these questions. I'm gonna go over the notes as I go over the questions, just so we can kind of remember what we're doing. Okay. Remember, we have two types of bonding: intermolecular and intramolecular. Okay. We don't really care about this. Okay. This is the important part. Okay. Intermolecular forces. What connects two molecules together? Okay. Like this. Okay. What connects these two together? Okay. Basically, that's the whole point of intermolecular forces. You have a few type of intermolecular forces. Okay. The first one, because we have different compounds, right? Let me look for something one second. Okay, I found this. Basically, crystals can be molecular, ionic, or atomic. Okay. If it's molecular, you guys know what a molecular is: non-metal plus non-metal, right? Covalent bonds. It can be ionic if it's non-metal plus metal, صح? It can be atomic when in network solids and metallic solids. Okay, because why? The basic unit here is one atom. Okay, and here the basic unit is just one metal. Okay, like lithium, I don't know, calcium, magnesium, and so on and so forth. But it's harder for you to find these metals, because that's a whole another story. It's a different chapter, metals. Anyways, let me not yap. My point is, what's my point? Yeah, it will be metallic when it's made out of one atom, single atom. Okay, ماشي. Where I think this is pretty self-explanatory. Let's take a look here. So metals, اتفقنا metals is when it's made out of one singular metal. They're made out of metallic bonds. I remember explaining. Wait. I don't know how I can't find it, but anyway, metals are made out of هيك 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, whatever, and so on and so on. These are all the metal ions. Let's say, I don't know, Na plus. Okay, repeated. In between them, you have electrons floating around. Okay, we call this the delocalized, or no, sorry, C of delocalized, okay, electrons. I'm gonna explain them all the bonds one by one. طيب, مش نحن the sodium is positive, مش the electron is negative. What happens in metals? مش sodium is a metal, right? It loses an electron, becomes positive. طب مش it has electrons floating beside it. طب what happens? What does the electron do? Doesn't it attract it? Yes, it attracts it. That's what we call a metallic bond. A metallic bond is a type of what we call an electrostatic bond. Okay, why electrostatic? Because the electric charge. Okay, that's a metallic bond. They actually asked you in the CA to label the metallic metal compound. Ionic compound, same thing. مش sodium loses, مش Cl gains, مش positive, مش negative, مش they attract. Yes, why? Because of the ionic bond. And what is the ionic bond? Again, it's an electrostatic bond. Okay, in case they ask it. Non-metal elements, van der Waals. Okay, قول عندك I don't know, hydrogen, H2. Okay, hydrogen bonded to a hydrogen. This is what we call a van der Waals bond. Okay, van der Waals is just any element bonded to another one. Okay, any molecule bonded to another. Come in, like let's say you have H2O, HO, heck, right? Okay, let's say it's bonded to another H2O. What bonds them is what we call a van der Waals. Okay, what do you need to know about VDW, this van der Waals? Okay, you need to know it exists between molecules. Okay, you need to know it exists between molecules. Okay, what else do you need to know? You need to know it's weak. Okay, can easily be broken. طيب. So when the forces, okay, I'll come to that later. Okay, that's what you know about van der Waals. You can read over the notes if you want. And then the network solids, they have covalent bonds. Okay, مثلا carbon bonded to carbon, bonded to carbon, carbon to carbon, and diamond. We're gonna go over each one by one. Molecular compound, again, and either the molecular ones like here. Okay, there, what? Van der Waals. Okay, these elements bonded together, these ones are the noble gases. Okay, noble gases form compounds. Okay, like this, and they're monoatomic. Okay, so you can just find helium floating. Okay, how do they bond to each other? Like I told you, van der Waals. And then polyatomic, such as sulfur, let's say S8. How do you bond to another sulfur? with the van der Waals. Okay, so the only things that use van der Waals are any elements on their own or molecular compound. طيب, this is all easy. Okay, we're gonna come back to everything later. Okay, anyway, let's start. Explain the following observations. Sulfur melts at a much lower temperature than graphite. Here is what you need to know and take it as a rule, and every chemistry teacher says the same thing. For a written part, you're probably, I haven't seen the past papers, any question that says explain a physical property, مش melting point is a physical property, okay? Any question that asks you to explain why, it always comes down to one reason, and it's the bonds between the intermolecular bonds. Okay, intermolecular bonds. Okay, why? I'll explain it in a very easy way. Let's say you have carbon, and diamond. These are all covalent bonds and they're strongly bonded together, right? Okay, let's say عندك هلا مثلا ice. It's isn't it H2O? It's H2O, right? Bonded to another one. Let's say this is ice. Honestly, this is the first thing I thought of. طيب, how are these two bonded, the carbons, to form the diamond? By covalent bonds, like strong covalent bonds. How are these waters bonded, these ice molecules bonded? Van der Waals bonds. What do we say about Van der Waals? Isn't it a very weak bond? صح? It's a very weak bond. Okay, actually you can see VW, very weak. What does that mean? Which one should be easier for me to melt? The one that has weak bonds or the one that has strong bonds keeping them together? Obviously the one with weak bonds. Okay, so anytime it tells you something like, okay, why would, I don't know, they give you a random element, anesthesia, I don't know, so some random ass name from chemistry, and they tell you, oh, this melts at a really low temperature. Explain why. You don't even need to know what the element is. If it melts at a really low temperature or it boils at a really low temperature, you should immediately know that the intermolecular forces are weak. Okay, so let's see the solution they put for me. Sulfur has van der Waals forces between the molecules, but graphite is what? You guys know graphite is what? Carbon, huh? We're gonna touch on network solids in a bit, I think, right? Yeah, over here, network solid. Okay, we're gonna come to it later. Exactly, but you should know that over here, diamond and graphite are network solids. Okay, you should know that. They're made out of carbon. We're gonna go into detail on them later. Let's stay here now. Anyways, so we said graphite has covalent bonds, and then VDW between its atoms. Okay, again, I'm gonna explain this later, but for now you need to know that sulfur, it's just one atom, so of course it's gonna have VDW, but graphite has covalent bonds. We know covalent is stronger and harder to break than van der Waals, so sulfur melts at a lower temperature. So if I were to mark your paper, what would I ask from you? What would I see I would want marks for? I would give 1 mark for this. Okay, especially this sulfur has VDW. I would want 1 mark on that. I would want 1 mark on this. Okay, this isn't really necessary. You can say it, but you need to say this is 1 mark here, 1 mark here, and then a comparison for your 3rd mark. Covalent bonds are stronger and harder to break than VDW. Okay, that's how I would mark this. طيب, يلا, easy. What else? Question 2 until 7. طيب. Explain why phosphorus is a brittle element while diamond is hard. Again, just so you don't know, if you don't know, brittle means easily broken. Okay, easily broken. Why would something be easily broken while another element is hard? Same exact solution as part 2, as question 2. Same thing. The intermolecular forces of attraction are weak. Phosphorus has weak VDW between its molecules, which are easy to break, so it's brittle. But diamond has covalent bonds, so these are strong and difficult to break, so it's hard. It's common sense. Like you're building a base. Instead of wood, you're using metal. Wood being the VDW, the metal being the covalent bonds. So this is really, you don't need a basic understanding of chemistry to understand this. Like any joker, any 5th grader, I think, would understand this. If you told them, okay, this has covalent, this has VDW, okay, VDW is stronger, VDW is weaker, covalent is stronger, which one do you think will be easier to break? He will tell you, of course, the one with the weaker bonds, phosphorus. It makes sense. Really, it makes sense. Explain the following observations. Sulfur is a non-conductor element while sodium is a conductor of heat and electricity. This is the 3rd property I need to explain. We explained melting points and boiling points. We explained brittle and hard. في كمان I remember they had like a place where they explained properties. What's this? This is no, this is just hold up. Okay, yeah. So basically, everywhere for all the properties, it explains why. When you state a property, you need to be able to explain why. Okay, من الآخر. I have to let you know. خلاص. Okay, cool. Metals have high melting and boiling point. طيب, okay, why? Okay, thank you, but why? Explain why. Okay. You could see a question list and explain 3 properties of metals. You have to listen to explain 3. Okay. We already touched on melting point and boiling point. Okay. We said if it's a weak melting point and if it's a low melting and boiling point, that's because the forces are weak. But over here in metals, they have in metals, what was it? It was metallic bonding, right? So I'm just giving an example. If you were to see a high melting point and boiling point, it's because obviously strong bonding. Okay, ignore metals now. But in general, if you see high melting point and boiling point, it's opposite to what we just solved. What we just solved was low, so it will see weak. If it was low boiling point, melting point, it will be weak force. But if it is high, strong bonding, right? Type. And this energy part is also kind of important. Just understand it, conduct heat and electricity. I'll come to this last. Malleable and ductile, okay? If malleable and ductile, I'll also come to this in a second. Shiny and lustrous. Okay, shiny and lustrous, I'll explain it. Only metals are shiny, okay? I'm pretty sure. Why? Why are they shiny? Because electrons can absorb and re-emit light. Okay, that's it. What did we say about metals? How do they look? They drew it for me up here. And this, by the way, this exact thing came in the CA, this picture. This is metals, right? We said metals are surrounded by electrons, right? طيب. These electrons, what do? They actually absorb light and re-emit it. Okay? So that's why actually they are shiny. Okay? هلا these two, conductivity and electricity, and malleable and ductile. Malleable and ductile, as they conduct heat and electricity. To conduct heat and electricity, what needs to flow? Electrons, right? So if you ever talk about in chemistry, physics, anything, you want to conduct electricity, you need to say there's some moving electrons, right? Type. In metals, do you have free electrons? Do we? Let's take a look. Didn't we say this is a sea of delocalized electrons? Yes, delocalized and free. Okay, so that's why metals conduct electricity, because they have a sea of free electrons. Okay, and these are free to move. Malleable and ductile. What does malleable and ductile mean? Basically means you can smash it and make it into wires and tubes and whatever. You can change its shape. When a force is applied, the layers of positive ions can easily slide over one another. Okay, the attractive forces in metallic bonding act in all directions, so when layers slide, new bonds are easily formed. Okay, this is a good example over here. When you smash it, as you can see here, these bonds are all moving, electrons are moving everywhere. Since it's very easy, these can just slide above each other, and the electrons can come here and replace the ones that were there. So it's basically, it's very easy. Okay, as you can see here, before, after you push it, new bonds will form. Okay, very easy. So that's this one. There was one also brittle. Can we واحدة brittle? 100%. I saw one that's brittle. Brittle, yeah. If you see brittle, it's also due to the bonds. Okay, due to its structure. They're positive for. Okay, same thing we did here. Okay, so when we said something's brittle, it's because it's weak VDW. Like, weak bonds cause it to be brittle and break. Explain 4. Sulfur is a non-conductor while sodium is a conductor. Type. What did we say? To conduct, what do you need? You need free electrons. Type sulfur, isn't it an element? Right? It's an element. So it's bonded by what? VDW. Right? So is there any electrostatic forces? Is there any free electrons? No. So what do you say? There's no free electrons in sulfur. But in sodium, isn't it a metal? Yes, and we said metals have sea of free electrons or delocalized electrons, whatever you would want to call it. Okay, so let's take a look. Sulfur is non-conductor because it has no free ions or electrons. Sodium is a conductor because it has a mobile sea of electrons. Okay, You could say mobile sea of electrons, you could say sea of free electrons, you could say sea of delocalized electrons. They all mean the same thing. Explain why silver is a shiny element. Isn't silver a metal? Right? Ag, it's a metal, right? Type, okay, what did we say metals have in the electrons to make it shiny? The electrons absorb and re-emit the light. Okay? Explain why sulfur is brittle while copper is ductile and malleable. Sulfur, what are the bonds between them? Van der Waals, right? So brittle, so it breaks easily. However, copper is a metal. It's ductile and malleable. Why did we say something would be ductile and malleable? When smashed, we said they can slide the copper ions can slide over each other and form new bonds. صح? Let's take a look at the answer key just so I want to make sure. Silver is a metal that has metallic bonding, so delocalized electrons can absorb and re-emit light energy, which is visible as a shine. Okay, if it comes written, please say it has metallic bonding that has electrons. Okay, just mention the metallic bond. Question 6. Sulfur has weak VDW, so it's weak, so when a force is applied, it breaks. Okay, copper has metallic bonds holding its atoms together. These are non-directional bonds, so it can be deformed without shattering structure. Okay, they said this or this. Now we took this, right? We said copper is a metal with metallic bonding, so when smashed, the copper ions can rearrange, slide over each other, and form new bonds. Okay, copper has metallic bonds holding its atoms together. These are non-directional bonds, so it can be formed. Okay, it's good to know that. Kevin, it's good to understand this second one here. They're saying that copper has non-directional bonds. Okay, so it can be formed without shattering its structure. في bonds like diamond مثلا, or no, sulfur. Okay, S8 bonded to another S8. There's a specific angle actually, at which they bond. I'm not sure it's this specific angle that I drew here, but my point is there's a specific direction for the sulfur bond. Okay, and when you smash one sulfur, when you tweak the direction a bit, since it's directional, the whole molecule will fail. Okay, so you need to know that metals are not directional bonds. Okay, in case they ask them, these are all things that could come in the multiple, but you don't usually see this. This is the more used one. Give 4 general properties of metals. Let's start. First one would be, let's say, conduct electricity, conduct heat and electricity, right? The second one would be it's shiny, right? The third one would be high melting point and boiling point, right? And the fourth one would be, let's think a bit, conduct heat and electricity, shiny, high melting point and boiling point, maybe malleable and ductile, right? Let's explain each one quickly. Conduct heat and electricity due to the presence of free mobile sea of electrons, right? Shiny, why is it shiny? Because the electrons in the sea of electrons absorb and re-emit light. High melting point, boiling point, why? Because the presence of strong covalent bonds in between the molecules that are hard to break, so it's going to require more energy, so it's going to be a higher melting point and boiling point. Malleable and ductile, why is malleable and ductile? Because the bonds are non-directional. You can say either the bonds are non-directional, or because when you smash it or hit it, the cations or the metal ions will just slide over each other and form new bonds. Okay, we skip question 8, 9. Oh no, you told us. Oh no, we skip question 8. Continue to 9. Okay. Germanium has a similar structure to that of diamond. Describe the structure of germanium. Okay, so to do this, you need to describe the structure of diamond. To do this, I'm gonna quickly skim over network solids. Network solids, you need to know that basically it comes from an atom, like carbon. You can form graphite out of this or diamond. These are both coming from carbons. Okay. Diamond and graphite are what we call allotropes. Okay, why? Because they both come from carbon, but they have different structures. Okay. So this always comes. What are allotropes? And what are examples of allotropes? Diamond, graphite, and Buckminster fullerene. Okay. Whoa, what the fuck? Okay. Whoever wrote, I think the regional wrote She put a hyperlink on physical state. If you click it, it takes you to a different link. Anyways, let's start with diamond. I'll skim over it very quickly. Okay. Diamond. Okay. You need to know diamond has a tetrahedral shape. Okay. Tetrahedral looks like this. One bonded, one here, one here, one here, one here. This is called a tetrahedral because if you join the corners, you get this shape. Okay. It looks like this. You see? It's kind of like a tetrahedral, like a pyramid shape-ish. Okay? Type. You need to know one carbon is bonded to 4 others at any instant. Okay? Each C atom is bonded to 4 others. Arranged tetrahedrally. Okay? What do you need to know about the properties of it? Diamond. Akid, it has high melting point. Akid, it's very hard. It's not brittle. Akid, why is there... Okay. There's no electric or thermal conductivity. This one I'm going to explain it a bit because I think it may be required. But I'm going to explain it just so you understand. Why doesn't diamond conduct electricity? Many people actually in our society, they have the idea that diamond is a metal and it conducts electricity. It's a metal, right? No! Diamond is made out of carbons. نحن اتفقنا one carbon is bonded to how many other carbons? 4, right? Type. From chapter 8, carbon has a charge, has 4 electrons in its outer shell. So when it bonds, how many electrons does it need to complete it? It needs what? It needs 4 other ones. Okay, if it bonds to one here, one here, one here, and one here. طب هلا how many does it have? It has 8. So is there any free electrons? No. خلاص, it has a full outer shell. You're going to see now in a sec, with graphite, it can conduct electricity, and that's because graphite actually has a free electron. I'll come to it in a second. Okay? So, very easy, very high melting point, obviously, because strong covalent bonds. Carbon bonds are very strong when it's full shell. Very hard. Obviously, the bonds are rigid. You guys know diamond is very hard. And obviously, no electric or thermal conductivity. Graphite, okay? Graphite is a bit interesting, okay? Graphite is almost the same thing, but you need to know it's instead of being bonded to 4, now you're bonded to 3, okay? And it looks like a triangle. So if you connect the 3, it's bonded to, okay? Connect them, it looks like a triangle, as you can see here, okay? Anyways, so it looks like a triangle. Each graphite layer is considered a 2-dimensional giant, okay? You need to know about graphite. It's 2-dimensional. So you have layers, okay? Let me explain. These ones here are held by covalent bonds. But to connect to another layer, there is VDW forces. Okay? So that's why, in your opinion, what do you think? Is graphite stronger than diamond or weaker than diamond? Obviously, it's going to be weaker because here, it's a bit weaker than diamond because there has VDW forces. So, graphite, I'm sure you guys know your pencils are made out of graphite. So, if graphite was hard and not slippery and not I don't know, whatever, easy to move, do you think you can write with it? No, right? So, what do we need to know here? It's held together by weak forces of attraction. That's why the layers here can slide across each other. Think always graphite, think pencil. Graphite is soft and slippery due to weak forces of attraction. Graphite conducts electricity. Akid, why? Because since now graphite were bonded to 3, what does that mean with the carbon? We need 3, carbon has 4. 1, 2, 3, 4. If I add 3 هلا, bish I have 1 left free, صح? So I will have some free electrons, okay? It's gonna have 1 free delocalized electron, so that's why you're actually gonna conduct electricity. Graphite has a high melting point, akid, because we have strong covalent bonds. Even though they're slippery, it's still a high melting point. But when you think graphite, always think pencil. Think pencil. Pencil is soft and slippery. Why? Because of VDW. Pencil, okay, if it's soft and slippery and do you think it can conduct electricity? Of course it can. Since it's soft and slippery, it can kind of move around. If I think about it like that, okay, because why can it conduct electricity? I told you anytime something conducts electricity, free electron. Graphite has a high melting point. Obviously, it's a network solid, so it's gonna have high melting point because of the strong covalent bonds. Okay, these are comparing diamond and graphite. You can read over this if you want. But these uses, you need to know them, okay? Diamond is jewelry, glass cutters, drill bits, diamond saw, rock borers, abrasive material, anything hard, okay? Graphite used furnace lining, electrodes, lubricants, pencils. Pencils is important, huh? Okay, last network solid is silicon dioxide. Okay, it looks similar to diamond. Okay, however, it's not. Silicon dioxide is SiO2. So uh, each silicon atom is bonded to 4 oxygen. Okay, okay, yeah. Silicon bonded to 4 oxygen, as you can see here, and each oxygen is bonded to 2 silicon, as you can see over here. I need to use a different color. Let's take yellow. Yeah. Okay, as you can see here. طيب, what do you need to know? It also follows a tetrahedral structure. صح? The same structure as diamond. Tetrahedral. شايفين? Let me use a different color. I'll just use yellow. 1, 2, 3, 4. Join them. 1, 2, 3, 4. As you can see here, that's a tetrahedral bow. What else? It's a tetrahedral structure where every silicon atom is strongly covalently bonded to 4 oxygen atoms, and every oxygen atom is conjugated. Yep. Okay, properties. It's very similar to diamond. Okay, احفظون. Uses microchips for computers. خلاص. Let's go back to our course division. Germanium has a similar structure to that of diamond. Describe the structure of diamond. What do we know about the structure of diamond? And I know a lot, but I'm not sure what to say. I don't want to say anything and confuse you. So let's just take a look at the answer key. Germanium exists as a giant structure. We know obviously diamond is a giant structure, right? Network solid. So what is the structure? Don't say network solid, say giant structure. Where each germanium atom is strongly and covalently bonded to 4 other germanium atoms in a tetrahedral arrangement. The bonding is extremely strong. So, germanium, what do we know about diamond? Isn't it a strong structure? Giant structure? Yes, because we said carbon, blah, 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 right? No, so on and so on, so forth. Each carbon in a diamond is bonded to how many other carbons? 4. So, same thing with germanium. Germanium, I think it's Ge, is bonded to 4 other germaniums as well. Okay? But what about the bonds? The bonds in diamond, are they strong or weak? Actually, they're strongly and covalently bonded. What's the shape? Tetrahedral. And it's extremely strong. Type, let's take a look. I think part B they ask about SiO2. I can kind of look at it, kind of see it. SiO2, silicon dioxide, has a similar structure to that of diamond. Describe the structure of silicon dioxide, and you may use a diagram. When I draw a diagram, I'm going to show you the diagram, of course. Without looking at the answer key. SiO2, what do we know? What do we know about the structure of silicon dioxide? We know that it follows a tetrahedral structure. We know that it forms a giant structure. We know that each silicon is bonded to 4 oxygens, and we know that each oxygen is bonded to 2 silicons, and we know these bonds are strong and covalent bonds. Okay, so let's take a look. Silicon is a giant covalent molecule. I wouldn't say molecule. I don't know. Every silicon atom is strongly and covalently bonded to 4 oxygen. Every oxygen atom is strongly and covalently bonded to 2 silicon. Right? We said this. The ratio is 2 silicon atoms to 4 oxygen atoms, or simply 1 silicon atom to 2. Right? SiO2. يعني أكيد. SiO2. 1 to 2. The ratio is, know it if they ask you. Oxygen atoms, as you can see from the structure below. Let's take a look here. You can see Si bonded to 4O, and then each O bonded to, it should be 2S. 1 here and 1 here. Okay? You can see here. If you want, if they ever, I don't know, maybe they might, I don't know, but if they ask you to draw, here's what I would advise you to do. 1 here, okay, 1 here, okay, 1 here, okay, and 1 here. Okay, because here, if you connect them, هيك 1, 2, 3, yeah, this is a tetrahedral bonded to 4, right? And then if you want to continue, add just another Si, because now this is bonded to 2. And if you want to continue here, but you won't have space, let's continue here. مثلا you can add an Si here. Okay, just giving you ideas. مثلا يلا, let's continue. Question 10. Specify the major intermolecular forces that exist in the crystal of each of the following compounds: CH4, HCl, CO2. Okay, we're gonna first state what the nature is for each one and see. CH4, it's, by the way, this is methane, but that's for topic 5. Let's stay in chapter 9. This is obviously a molecular one, right? Because we can't see any metal with non-metal. These are both non-metals, so it's molecular. So it's gonna be covalent bond. Right? HCl is كمان molecular, so it's gonna be covalent bond. CO2 is كمان molecular. molecular, I don't know. So covalent bond. NH3 is كمان molecular. So it's gonna be covalent bond. Hydrogen fluoride is كمان molecular. So it's gonna be covalent bond. NaCl is what? NaCl is ionic. So it's gonna be ionic bond. And the last one, SiO2, is a network solid, right? Network solid. But we know that the bonds in a network solid are covalent bonds. Not, yeah, they are covalent bonds, but does it have VDW? No. I think VDW is one of the answers because I saw it. Okay. I think. Okay. Okay, well, we got the general idea. I think they want us to elaborate a bit. Okay, let me read over this and try and understand this. Okay, أنا المشكلة I didn't read it. I'm giving you covalent bonds, but that's within the molecule itself. What I gave you was, by accident, sorry, was the intramolecular forces. Okay? That was intramolecular, what I gave you. Here they're saying intermolecular. Intermolecular, don't forget, intermolecular is within the molecules. فمثلا between one molecule of CH4 and another molecule of CH4. How is it? Okay, what do we know? Between molecules, this is obviously a molecular structure, right? Molecular. So between two molecules, what is it? We said it's van der Waals, right? Between two covalently bonded molecules, it's a van der Waals. Insert in here, حتى molecular compound. HCl, okay, and CO2. HCl, I think is dipole. Okay, I had to read this for a good 10-15 minutes. Basically, intermolecular forces, as we said, van der W. You know, we're expecting it to be cute and petite like this, yeah? Van der W, ionic, covalent. But it isn't, no. Okay. I explained this before in one of my CAs, but basically bonds, okay, for molecular bonds, okay? Okay, so here they're covalent, but we have two types, non-polar and polar. See, they don't ask a lot about this, but it's still in the course division specified. So if she brings it, she has every right to say it was in the material, okay? Non-polar. Non-polar basically means it's the same element bonded to another. O2, I don't know, H2, F2. These are all non-polar. Polar is when you have two different elements. Okay? Different elements. What do you need to know about this? What do you need to know about polar? We call it dipole. Okay? Well, let's give me an example. HCl is dipole. CO2 is polar, has polar, but or no, it's not polar. It has dipole, but it's not polar. ليه? Because although one can be polar or be considered under this category, the structure of the molecule matters. CO2 looks like this. This one cancels with this one, and you're left with non-polar. Okay, so what will CO2 have? Just van der Waals. Okay, so CH4 also is van der Waals. Why? Because CH4 looks like this. Which they cancel out, you're left with non-polar. Okay, so knowing this, let's answer this question. We know it's molecular, so the bonds can be polar and non-polar. Since they're different molecules, you're gonna say it's polar. But what do we know? Is it gonna be actually polar? Let's take a look. Is it polar? CH4, think about it. CH4. Okay, these cancel, so you're left with C. So it's not polar. So what bonds are left if it's a molecular structure? What else يعني شو في غير البولر الدايبول VDW. HCl is just H bonded to Cl. Is anything cancelling out? No. So we say it's dipole, dipole. Okay? CO2, we said they cancel out, right? So what other, if it's not dipole, dipole, what is going to be? VDW. Okay, that's how I solve. NH3, holic, these two are special cases, okay? We're going to take them to the side here. There's another type of molecular bonding called hydrogen bonds. Hydrogen bonds happen for these elements. Okay, memorize it for these. Okay, anytime you see hydrogen with this this element, it's gonna be a hydrogen bond. Why? Because they have high difference in electronegativity. This is something that will be explained in grade 12. That's not the point now. So anyway, these two are hydrogen bonds because it's hydrogen with NO or F. NaCl, it's obviously it's ionic, and SiO2 is a covalent structure because it's an atomic solid. Okay, so for the most part, they're okay. So as you can see here, these are the answers. Just memorize this if you want. Carbon dioxide comes a lot. Okay, they like to ask carbon dioxide. They say, is it polar or non-polar? You say non-polar. Okay, or no, you say polar. There's a question in the course revision. Wait. Yeah, so like, see, it was in chapter 8. CO2, does it have polar bonds? Is it a polar bond? I'm telling you, they like to ask about it. This was in chapter 8, but just to go back and show you. Yes, they do have polar bonds, but it's not considered as a polar molecule because they cancel out. Okay, so let me just scroll up. Yes, it's considered polar, but is it a polar molecule? No, because they cancel out. Okay, let's go back down to chapter 9. So question 11. What? Where are we now? Question 11 to 14. Type. We skip 10. Oh wait, I was supposed to skip 10. Shit. My fault. I'll put a note in the. I'll put a note when I send a message. Question 11. Magnesium reacts with chlorine to form magnesium chloride. In the lattice of magnesium chloride, the ratio of magnesium ions to chlorine ions is 1 to 2. Explain the term lattice. When you see lattice, it's basically like a crystal, okay? So it's a regular pattern. Anytime you see lattice, you have molecular lattice, whatever. Okay, but actually, no, you don't. Lattice is for ionic compounds. It's basically a pattern of positive and negative ions, okay? How does it look? It looks like this. 1, 2, 1, 2, 1, 2, 1, 2. Okay, it looks like this. And then these are obviously bonded like this. You get what I mean? Okay, question 12. Describe the structure of solid CO2. I2, KCl, diamond, H2O, Li, SiO2, X, and Xe. Are they made of ions, giant structure, or separate molecules? Let's start with CO2. If it was a solid, it's obviously going to be a molecular solid, right? I2, it's an element, again, it's going to be molecular solid. KCl, it's ionic, right? Diamond, it's a network solid. A network is just giant molecular, by the way, okay? If they put molecular as an option and not a network, then you say molecular عادي. Okay, H2O is molecular أكيد. Li is metallic because it's a metal, right? Xe is a noble gas, so we say it's molecular. Okay, SiO2 is network solid. Okay, let's make sure. Let's check the answer key. Molecular, ionic, and network solid, molecular, metallic, atomic. They call this atomic. Okay. Yeah, makes sense. Because Xe, like I2 is correct molecular لأنه it's molecules of I2 bonded together, right? طيب هلا Xe, it's atoms of Xe bonded together. So when you see just one single atom, we call it atomic. Li is atomic, but since it's a metal, we don't say it's an atomic structure. We say it's a metallic structure. But in general, a metallic structure is just another atomic structure. Okay? طيب. What are the particles making up the lattice? A molecular lattice, what makes it up? Do you mean bonds? Okay, the actual particles. Okay, what makes up CO2 bonded to CO2 bonded to CO2, this huge solid? What makes it up? أكيد the molecules of the CO2. What makes up this I2 bonded to the I2 bonded to the I2? Obviously, again, iodine molecules. KCl, this is where it starts to get a bit tricky. KCl bonded to KCl type. But it's a lattice, it's K plus Cl minus. For Ionic compounds, you can't say it's made out of molecules or ion. You can't say that. You have to say ions. Okay. So is it ions? Yeah. Okay. Diamond. مش it's a network solid? Network solids, what's it made out of? Isn't it made out of this? Carbon, 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 repeated, 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 repeated. Yes. So will you say it's a molecule being repeated? No, it's a carbon atom. So network solids are actually atoms being repeated. H2O, it's molecules of water being repeated, obviously. Lithium, again, it's just atoms, right? Xe, it's atomic, فأكيد is going to be atoms. SiO2 will be, I think this one's molecules, صراحة. Let me check SiO2. SiO2 is atoms. Type. Li is, okay, I'll come back to Li. So let's see. Any network solid is atoms. Type, because at the end of the day, it's an atomic solid. Type, what did we get wrong? We said these are correct, these are correct, these are correct. عادي عادي كلهم عادي. Okay, but for lithium, the ما عجبهم الميتals. Sorry, for the metallic, ما عجبهم الatoms. Okay, atom is correct, but let's elaborate more. What's the particle? It's positive metal cation, right? What's a metallic solid? At the end of the day, what's a metallic solid? مش اتفقنا it's Li, 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 and I feel electrons bonding them together, right? It's just a positive metal cation. What else is inside the lattice? What's it made up of as well? It's made up of electrons as well. Okay? 13, 14, صح? A. Okay. Part A, question 13. The following table is a list of electron distribution for atoms of certain elements. From the above list, choose an element that is a noble gas. Okay? For this one, some of it you're still not supposed to know, but I'm gonna talk about it. Because it's part of a different chapter. Obviously, that is a noble gas, it's gonna be D. Soft metal with a low density. You need to know this is actually group 1 elements. Okay? It's not required for your periodic, but she put it here in the course division. I don't think she's gonna bring it because it's part of chapter 10 metals. But know it. Okay? So it's gonna be E. It should be E, right? Let me see. To be able to self okay, yeah, okay, we got this wrong. Yeah, so that's correct. Can form a covalent compound with element A. Okay, form a covalent compound with element A. Let's see. Okay, to form a covalent compound with A, that means we're gonna share some electrons to A. Okay, let's take a look at B. Can B share? A needs 3 more, right? Can B share 3? Yes, it can. It has 4. C, can it share 3? No, it only has 2. D, you can say, oh, it has 8, فأكيد it can share. No, if it has 8, it's stable, it won't share at all. It's already يعني كامل. E has 1. Can 1 give 5 and become 8? No. F has 7, so it can share 3. So it's gonna be B and F. Very easy. Has a giant molecular structure similar to diamond. What is diamond made out of? Carbon. Carbon has 4 electrons, by the way. So which one is gonna be? B. It should be B, صح? B. And then the last one can form a negative ion of the type X3 minus. Type, which one here is gonna gain 3 electrons? Akid it's A. Yani, I think this is very easy. Why is it A? Someone may ask me. I need to explain. I forget to explain. It has 5. Which one? Yani, if it's gonna gain 3 electrons. X3 minus. Yani, it gained 3. Right? To get how much? How much is our goal? Our target always 8. Right? So how much did it have originally? 5. Very simple and easy. Elements C and F form an ionic compound. Okay. C and F? Really? How? Okay. Draw a diagram that represents the formula of this compound, the arrangement of the valency electrons around the negative ion, and the charge on the ions. Use X to represent C and a dot to represent F. So this is more chapter 8 actually, but عادي, let's do it. C اتفقنا it's an element, let's call it C2 plus, right? Because it's gonna lose 2. F has 7, so how much is it gonna gain? 1, so let's just call it F minus. طيب, let's do crisscross. How much are we gonna get? We're gonna get CF2. صحيح? Right? We're gonna get CF2. So they said the formula is CF2. They said draw a diagram that represents it. CF2, yani you have C here, and you can say F here. Wait, no, it's an ionic compound, صح? In the marking scheme, I just checked it. They want you to figure out what it is, by the way. So obviously, if you have a periodic table, I remember I have one. Wait. Yeah, for here, element C has 10, 18, 20 electrons. Let's just see what's atomic number 20. 20 is 10, 11, 12, 13, 14, 18, 20. So it's Ca. Okay, so element C is Ca. The first thing actually they did was actually figure out what C and F are, which makes sense. Okay, C is Ca. How about F? Let's take a look. 20 plus 36 as a 10 plus 30, 46, 46 plus 10, 53. Element 53 is iodine. Okay, so F is iodine. So this is what they did first, and then they did crisscross, which I guess makes sense. Okay, so this is the formula of it. How do we draw the diagram? Remember, to draw a diagram for an ionic compound, you draw them separately. You draw the last shell. Okay, since Ca is empty last shell, we're gonna draw it like this, right? And 2 plus. Okay, we have two I minuses, right? So we're gonna write I here. We know now it's what? Full shell. Why full? You know, it gained electron from calcium. So what do? We draw 7 circles and 1 X, right? And we're gonna put minus. Remember, it's I2, so we have two I's, don't forget. 1, 2, 3, 4, 5, 6, 7, 8 minus. This is how it looks. I think this is very self-explanatory. Question part C. Draw a diagram representing the arrangement of valence electrons in the molecule of nitrogen trichloride, so NCl3. Let's take a look here. This is I don't know why they put this here. It's chapter 8 stuff. NCl3, so it looks like this, right? Right, هيك. طيب, we know N has, we'll draw all our circles first. We know N has 5 originally, so we're gonna write 5, 1, 2. Oh no, they said use circle as, they said use X for nitrogen. Okay, so we're gonna use, it has 5 X's, right? 1, 2, 3, 4, 5. Type. Okay, no, that's wrong. The fifth one should not be with the chlorine. ما فاقق. Yeah, for 5. You know, let me redraw it from the start. Don't draw it how I did. Okay, draw the nitrogen. Draw it 5 electrons first. Okay. 1, 2, 3, 4, 5. طيب. You have 3 spaces for chlorine. You have a chlorine that can go here, here, and here. We know chlorine has 7. صح? Chlorine has 7. For what are we gonna do? We're gonna put 1, 2, 3, 4, 5. Can you put 6 here? No, you can't. 7, 6, 7. Same thing here. 1, 2, 3, 4, 4, 5, 6, 7. Nice and chill. Okay, then 1, 2, 3, 4 over here. 5, 6, 7. Very chill, very calm. Whatever. I think this is very easy, صراحة. Not too hard. Chapter 8 stuff. Explain why an aqueous solution of sugar is a non-electrolyte, while that of NaCl is a good electrolyte. Let's take a look. Sugar, we know, is a molecule. Can molecules conduct electricity? No. Always when something conducts electricity, when something conducts electricity, what is the reason behind that? The reason behind that is free electrons. So if we say sugar cannot conduct electricity, يعني معناتها it doesn't have electrons. خلاص, that's all you have to say. It doesn't have free electrons. Let's take a look. NaCl has free electrons within the ions. So an aqueous solution of NaCl is a good electrolyte because NaCl dissociates into ions that can move and carry electric current. By the way, it's not strictly electrons. It can be ions. Ions act like electrons. Okay? And by the way, the definition for the reason in the notes, by the way, for being a good conductor isn't just electrons. They said free electrons or free ions. They said or. Okay, for NaCl, for any ionic compound, it doesn't have free electrons, it has the free ions. Actually, that's what causes the conductivity of electricity. Aqueous solution of sugar contains no ions as sugar remains as molecule, so it is an electrolyte. I know my mic is working. Okay. Where am I now? Question 18. Yellow. Okay, let's finish. Not much. Whoa. Okay, عادي. It's okay. It's calm. It's calm. Explain why solid NaCl is a non-conductor of electricity while when melted it becomes a good electrolyte. Okay, اتفقنا. Same thing. For ionic compounds, we don't speak about the electrons. We agreed. For ionic compounds, you want to talk about conductivity. You don't talk about electrons. You talk about what the ions. NaCl, it's a non-conductor of electricity while solid, but when melted, it's electrolyte. Why? Because when it's solid, the ions are not free, but when it's melted, the ions are free to move. That's it. يعني, really. Let's take a look. 18. NaCl, it doesn't allow whatever the ions are held together, so no motion of the electrons. But when molten, the ions are free to move and therefore conduct electricity. Describe the structure of a network solid and give two examples on such solid. Let's talk about describe the structure. What? Oh, so saying in general. Okay, the general structure of any network solid, it's strong covalent bonds. You know what? No, I want to see the answer key because I'm not sure. How did they say it? Because it can be either one or the other. A network solid is a giant 3D structure. اتفقنا. With strong covalent bonds. اتفقنا. Okay. Where the shared electrons are localized, making the structure very rigid. They said localized, no? So it doesn't conduct electricity, making the structure very rigid. The chemical formula of such solids shows the simplest ratio of the atoms and not the total number of atoms per molecule. I think this is pretty obvious. If we were to show the total number of atoms per molecule in a network solid, and actually 500, 1 million حتى, you can go up to millions. Obviously it's going to show the simplest formula. Since diamond is just made out of carbon, we just call it C, because there's nothing else. Where each C atom is tetrahedrally bonded, and then silica SiO2. Okay, I think what they meant was describe the structure of a network solid and give two examples of that structure. Because since we took two different structures of network solids. We took the tetrahedral one, which is the diamond and silicon dioxide, and we took the triangle one for the other one, شو اسمه graphite. I think here they meant talk about one of them and give two examples, and obviously the only one we know two examples of is the tetrahedral one. Okay, and that one actually doesn't have conductivity of electrons. It doesn't have. Okay, I think this is pretty easy. Let's just read over the solution. Describe metallic bonding. Okay, metallic bonding. I'm gonna read over the solution and explain as I go. Okay, metallic bonding. You need to know. It's a good question. By the way, it's 100% gonna come. In a simple model, okay, you should know a metallic bonding. What is it? What's in metallic bonding? You have the positive cations that lost the electron, and they're surrounded by the mobile electrons. Okay, it's called metallic bonding. The electrostatic attraction between the cations and the sea of electrons is called metallic bonding. I told you metallic bonding is an electrostatic force, electrostatic attraction. Type. Very easy. Remember, metallic bonding, it was, let me show you the picture. It was this one. Okay, don't forget, positive cations surrounded by a sea of delocalized electrons or mobile electrons, whatever. Describe the structure of the solid ionic compound NABR. Ionic compound. What is the structure of an ionic compound? Isn't it a crystal lattice? Yes, it's a crystal lattice of repeated cations and anions. Okay, so let's take a look. It's a lattice of oppositely charged Na plus and Br minus ions, which each ion is surrounded by opposite charges, bound to them via electrostatic attraction called ionic bonding. Remember, any ionic compound follows this same rule. Any ionic compound has plus, then minus, obviously in circles, as a lattice, as it looks here. Okay, so you need to know ionic compound, crystal lattice. Guys, I can't explain this further, really. These are all memorizations. And how are they bonded? Akita, through ionic bonds. And why do ionic bonds happen? Because of the opposite charges. They're called electrostatic attractions, right? Positive attracts negative, right? Type. Question 22, 23, 24. Which of the following is not a common property for both diamonds and silica? Okay, silica is SiO2. They both form giant covalent structures. Of course they do. They're hard, yes. They both have relatively high melting point, yes. Each of their atoms is surrounded by 4 covalent bonds, okay. They both have a cage-like structure. Let's take a look. It should be It took me a second to think about it, wallah. But it's honestly, this is the only one that makes sense. Even if you weren't sure, this by process of elimination, part D is the only one left. Why is it part D? Isn't it silicon bonded to 4 covalent bonds and diamond, the carbons bonded to 4 carbons? What's this? Okay, exactly. What about the oxygen in SiO2? What about it? And like SiO, whatever, O, right? Double oxygen, isn't it bonded to another Si? خلاص خلصت السيمفونية. So is it bonded to 4? No, it's just bonded to 2 silicons. Okay, so you need to know this. Question 23. The table shows examples on macromolecules, covalent compounds, metals, and ionic compounds with some of their properties. Okay. So it basically gives us electrical conductivity when solid, electrical conductivity when liquid, soluble in water, melting point, boiling point. These are nice. Which substance is a metal? Obviously, the substance that is a metal is going to be the good conductor, right? So the substance that's a metal should be E, conducts when solid. Which substances are ionic compounds? Ionic compounds first should be what? Soluble in water, right? And when they're soluble in water, should they are they conductors in water or no? Yes, they are. And they are good conductors in water, right? A and B. مش فار yeah. Okay, A is obviously correct, but B is correct as well. Why? Because ionic compounds, remember, ionic compounds مش ضروري كلهم not all of them are soluble in water, such as, let me think of one. CaCO3 مثلا. CaCO3. This is not it's not ionic, wait. Okay, مثلا be a SO4. This is not soluble in water, but it's still ionic. Okay. Anyways, this whatever. That's what the AI gave me. Anyways, as long as you see conductivity when it's a liquid, that is what do you call it? An ionic compound. This is why isn't it? You're gonna tell me why is it E? You said good conductivity. It's a metal because it's also a good conductor when it's a solid. Okay. When it conducts and it's a liquid, but it doesn't conduct when it's a solid, it's an ionic compound. Okay. Explain your answer. Why does an ionic compound conduct when it's a liquid? Because we have to say because they conduct when they are liquids, and when they are liquids, they form free ions that can conduct electricity. Ionic compounds do not conduct electricity when solid, but they conduct when molten, right? Molten or in liquid, as melting frees the ions from their labs. Which substance conducts electricity in an aqueous solution? What do they mean, Yani? I think they mean A and B, right? It should be A and B. And I don't know how I'm saying B when مكتوب لي إنه it's not soluble in water. Of course, B is gonna be wrong. Yes. Okay. Why is B wrong? I think it's a trick question. I think they expect you to put B as well. Why it's wrong is because it doesn't form an aqueous solution. Okay. What's the only one here that can actually form an aqueous solution and conduct electricity? A, right? The only one that's soluble and conduct electricity in liquid is A. Okay. Nice, easy. For A is soluble ion compound. Okay. Which substance is liquid at room temperature? The room temperature is what? Like, I don't know, 24 degrees Celsius. Let's take a look around this temperature. Type melting point. So basically, which is the one with the, what's it called? Like, like, how can I say this? Okay, well, let's just test each one, okay? 24 degrees Celsius. Isn't this below the melting point? So doesn't that mean it's frozen at that temperature? So it's wrong, right? Here also, it's below 825, so it's wrong. 24, it's not below minus 95. Okay, okay, perfect. But is it less than the boiling point? Yes. So it's in between the gas and the solid state. It's going to be a liquid. So we're going to say element C. Here you can continue trying them all. Here, although it's not lower than the melting point, it's also greater than the boiling point. So that means it's going to be a gas at room temperature. Okay, room temperature, it doesn't necessarily have to be 24 degrees Celsius, but it's anything around 24, 25. Yeah, 25. So its boiling point is less than what? Which one did it take? D? What? And I skipped part D. I'm saying no. Yeah, which substance is a gas? We pretty much just answered it. We said it's D because 24 degrees, although it's higher than the melting point, so it's not gonna be a solid. It's also higher than the boiling point, so it's gonna be a gas. Okay, so the gas, it's D. Okay, which substance is a liquid at room temperature? We answered this, we said it's C. Why? Because although it's not a solid, it's also not a gas, since it's less than the boiling point. It's still here in the middle. Okay, this is gonna be C. Which of given substances is a network solid? Let's see. Let's think about it. Network solid. Relate network solids properties to the ones in this table. Melting point and boiling point of a network solid, we know they're high, right? Okay, we have a few ones that are high. So what about conductivity? Do network solids conduct electricity? No, right? Are they soluble? No. So which one is a high conductor? A high melting point, boiling point, but doesn't conduct? These two, we agreed that they are ionic, right? This one, we agreed it's... we didn't agree on it. We didn't say anything about it. But it can't be network because it has low boiling and melting. This one here, same thing. Low boiling and melting, but it can't be. This one has high, but what's the problem is that it's a good conductor. When network solids don't conduct. But the only one left is F. So F, because it has very high melting point and boiling point, but it doesn't conduct, even though. Okay? And then they said, okay, the student said that this is graphite. Do you agree with him and explain why? Now, what do we know about graphite? Well, okay, high melting point, high boiling point. What's the thing that differentiates graphite from everything else? Obviously, it's the ability to conduct electricity, right? So here, our network solid doesn't conduct electricity. So can it possibly be graphite? Obviously not. Okay, because graphite conducts electricity in the solid state, but here it doesn't. We're done with top 23. Our last question for this document, actually. Potassium nitride melts at 800 degrees Celsius. Nitrogen trifluoride melts at negative 200 degrees Celsius. Explain, in terms of attractive forces, why potassium nitride has a much higher melting point than nitrogen trifluoride. In your answer, refer to the types of attractive forces and their strengths. What did we say? Anytime we're comparing melting point, boiling point, any physical property, you need to always think about the bonds. At least think about the bonds. Okay? Yalla. Potassium nitride is K3N. Nitrogen trifluoride is NF3. طيب, potassium nitride, what's its nature? Metal, non-metal, it's ionic. NF3, isn't it molecular? Yes. طيب, it's molecular. Hello. What do we know about the bonds? What do we know about the bonds for ionic and molecular? Which one is stronger? Okay, let's take a look. We say K3N is ionic. Therefore, ionic bonds that are strong, right? NF3 is molecular. So it's gonna have polar, covalent. I won't mention polar. Let's just say covalent. No. In between the molecules. In between the molecules, right? Between the particles. What did they say here? Yeah. With weak intermolecular. Yeah, it's molecular compound. You can see molecular compound. Weak. What do we say for molecular compound? What is it? They didn't mention van der Waals, but you can say VDW. Okay, it has weak van der Waals bonds, which are weak. So therefore, K3N higher boiling point and melting point. Okay. Let's take a look here at the answer key. What did they put? The potassium nitride is an ionic compound with ionic bonding between its negative and positive particles. Nitrogen trifluoride is a molecular compound with weak intermolecular forces. By the way, if you ever see this means VDW, van der Waals. Ionic bondings are much stronger and they require much higher energy to break these forces. That's it. Thank you so much for watching and good luck.